So yes, I'm one of the philosophy tutors here at Pembroke, and most of my work is in the philosophy of physics. So I should probably start off by saying a little bit about what the philosophy of physics is, because probably not all of you have come across it before. So it's a discipline with a number of different faces. One of them attempts to look at our best theories of physics, relativity, quantum mechanics, and to try and understand what those theories are telling us about the world. So take quantum mechanics, any way that you cut the pie, it says weird things about the world. Some people think that it commits you to a multiverse. Other people think it commits you to very strangely behaving particles which behave non-locally. So what you do over here can instantaneously affect what you do really far away in a way which people regard as being problematic, and so on and so forth. So any way you cut the pie, things are weird. The task of the philosopher of physics is to try and figure out which of these options is the most palatable, which of these options is the best way to understand what quantum mechanics is telling you about the world. That's one kind of thing a philosopher of physics might do. There's another kind of aspect of the discipline, which is to look at our best theories of physics again, to look at claims which people make about the consequences of those theories. So for example, and this will be relevant to us, the claim that nothing goes faster than the speed of light, and to figure out whether those claims are true or not, and to really dig into the details about whether these are exactly right. And it's in that latter spirit that I'm going to be proceeding today. So I'm going to be focusing on exactly that question. Is it the case that things can go faster than the speed of light? And assessing whether it's true or not. And I'm going to spend a lot of time actually thinking about whether light itself always goes at the speed of light. So the way that I'm going to proceed is, first of all, I'm going to present to you the background to why people think this. How historically did we arrive at the view that the speed of light is invariant, that light always goes at the speed of light, and so on. Second, I'm going to present to you some recent work in physics, partly my own work, but partly the work of a bunch of other people as well, showing that the situation here is actually quite delicate, and it's not invariably and necessarily true that light always goes at the speed of light. And then in the last part of the talk, I'm going to talk about some of the consequences of this. So why should we regard this question as being important? I'd like this to be relatively informal, so I went for a blackboard setting rather than slides. If people have questions, especially questions of clarification as we go through, then maybe just stick your Zoom hand up and we can talk about it. Maybe let's save big questions to the end though. Okay, so with all of that background in mind, then let's get started. So there are kind of two ingredients that I need to input for us to understand where this claim that light always goes at this fixed speed comes from. The first ingredient is what's known as the relativity principle, which I'll just write here. This is a foundational principle in physics, which has been known for a very long time. So it was articulated in very elegant writings by Galileo. It was also discussed very heavily by Newton. But in fact, it goes back much further than that. So there was a philosopher and scientist called Yu Yi in Imperial China around 1000 AD, who also articulated the very same principle. And the principle is something that will be familiar to almost everyone here, probably everyone here. The idea is this. So consider some subsystem. Consider, for example, the hull of a ship. Philosophers call this Galileo's ship. Now, if I consider the ship at rest with respect to the shore, here's my shore, versus moving with uniform velocity, say v in this direction with respect to the shore, then I wouldn't be able to tell the difference inside. All of the physics would be exactly the same inside if this ship were at rest with respect to the shore versus moving uniformly with respect to the shore. People put this in fancy language by articulating the relativity principle as something like this. The laws of physics are the same for systems at rest versus in uniform translatory motion. And you'll be familiar with this as well in a bunch of contexts. So when you're on a plane eating your dinner, the plane's actually going several hundred miles an hour, but you don't notice. Nothing weird is happening once the plane is in the air and moving with a uniform velocity. Same on a train, aside from the mild jostling that you might get as the train goes over the tracks, you really can't tell what velocity the train is moving at. There's also a nice illustration of this when you pull out of a station, which you'll probably be familiar with. Sometimes you think that you're moving out, but actually it's the train next to you moving out, or vice versa. You really can't tell which of those things is going on. these are all illustrations of the relativity principle. Good. So that's the first kind of piece of the puzzle that we need on the table. By the way, Newton, in his Principia, this world-changing scientific book which he wrote, claimed to prove from his laws of physics that the relativity principle holds. So it's very closely associated with Newtonian mechanics as well. If you buy into Newtonian mechanics, then the relativity principle just drops out. That's his, for those who care, Corollary 5 in the Principia. Okay, good. So that's the relativity principle. The next thing that I need to talk about is waves. So we don't have to think about weird waves at this point. We can just think about very familiar waves: sound waves, light waves, water waves. There are some differences between these. So sound waves are longitudinal. The oscillations are in the direction of motion, whereas water waves are transverse. So the oscillations here are perpendicular to the direction of motion. But all waves have a very important property, which is that the speed of a wave is a function of the speed of the medium and not a function of the speed of the source. So that might not make much sense right now. Let me explain what that means. I think it's easier to think about the plane example. So a plane is going along. Here's our plane at some velocity. As the engines roar, sound waves come out. Now, what happens when the plane travels at the speed of sound? Well, we all know that then a sonic boom happens. The reason that this is happening is because the sound waves are actually coming out at a speed which is independent of the speed of the plane itself. They're only a function of the speed of the air, which let's take to be at rest. So the sound waves come out at the same speed, the speed of sound, regardless of the speed at which this plane is moving. When the plane hits the speed of sound, the plane hits these fronts, compressions from the sound wave itself, which is what causes a sonic boom as it hits a region of higher density air. The important point here is that the speed of the wave is independent of the speed of the source. Now, it's worth pausing on that. That's a property of waves, but you might ask, well, isn't there already a tension between that statement and the relativity principle over here? So if I'm in the plane and I hear a sonic boom, which you could hear inside as well, then doesn't that tell me something about my velocity? It tells me that I'm going in my plane at the speed of sound. And that's absolutely right. So there is a tension between the behavior of waves and the relativity principle. And it's already worth asking yourself, how do I square that circle? What people say and what people said when they were thinking about these things in the 1700s and 1800s is, you don't need to worry necessarily because the relativity principle regards fundamental physics. These sound waves, water waves, and so on, they're not fundamental physical phenomena. They're built out of, sound waves are built out of the compressions of very, very many fundamental particles in the air. Water waves are built out of, very complicated dynamics of fluids and so on. So it's at least not obvious that these emergent, apparent violations of the relativity principle actually spell doom for something like Newtonian mechanics, which, as I've already said, goes very closely hand in hand with the relativity principle. However, the situation would change if you came across a wave which really had the status, or you thought really had the status of being something fundamental. And that's where light comes along. So unlike sound and unlike water waves, light is supposed to be a fundamental wave, a fundamental physical object. People have known that light behaves like a wave since the 1800s with the work of Maxwell, the results of Maxwell's equations, Maxwellian electrodynamics, which show you that light behaves as a wave. But then if I've got a wave which is fundamental, would I not expect violations of the relativity principle? That's in fact exactly how people thought in the 1800s. So suppose that I'm on the Earth. This is this is me sitting on the Earth, and I fire light, which I'll say goes out at the speed of light. Well, if I'm at rest with respect to the medium of the light, by the way, we no longer think this medium exists for reasons that I'll get onto, but in the 1800s, people thought that just like sound had a medium, the air, water waves have a medium, water. So very naturally, they thought that light should have a medium, something which they called the ether. If I'm sitting on the Earth, then I should see the light going out at the speed of light. But if I'm moving at some velocity v, then from my perspective, this light should go at the velocity c minus v. It's kind of like, cars on a motorway. If someone goes past me at 70 and I'm going 60, then it looks like they're going past me at just 10 miles an hour. Same idea here, because the speed of light is a function only of the speed of the source, just like the sound waves in the case of the plane that I was talking about before. If I now imagine myself as someone sitting on this Earth when I know that it's going at velocity v, then I should see that light going out slower. That's what people thought, and a very reasonable thing to think. People then devised experiments which they thought would allow us to detect how fast we're actually going with respect to the ether, this medium in which light is supposed to propagate. In that way, we could figure out what our exact velocity is, which, just to recall, you shouldn't be able to do if the relativity principle holds, because the physics should be the same regardless of your velocity. In light of the fact that light is a wave, we think that, in fact, we can detect violations of the relativity principle, which is what people tried to do in the 1800s. So the most famous experiment of this kind was known as the Michelson-Morley experiment. And it works like this. Anyone that's studied undergrad physics will have come across this. So I have a laser source emitting a coherent, i.e. all of the same wavelength beam of light. The light hits a so-called half silvered mirror, which lets half of the light through and then reflects half of the light perpendicular. This light then bounces off two mirrors and goes back to the mirror, where it all passes through the mirror and detects what's known as an interferometer here. Well, if the reasoning that I went through on the previous slide is true, then if I'm going, or if this whole detector sitting on the Earth is going through the ether, this medium of the light at velocity v, then as the light goes this way, it should travel from the point of view of this detector at v plus c, v minus c, c minus v. And as it goes this way, it should look like it's going at c plus v. The overall amount of time that the light takes to go this way and this way should therefore be different to the amount of time that it takes the light to go perpendicular to the direction of motion of the ether. When I bring things back together again, there's no longer any guarantee that all of this light will be in phase, and I should detect interference effects. This is basically a fancy way to figure out what velocity I'm going with respect to the ether, depending upon the effects which I observe in this interferometer. But after Michelson-Morley did this experiment, people got very puzzled because they found that the result was always nothing. You always got a null result. You always got absolutely no interference effects. So what it looked like is that light was always going, from anyone's perspective, at c, contrary to the reasoning that I was going through on the previous page. And people really didn't know what to do with this. You know, light is a wave. We know that waves travel such that their speed is a function of the medium, not a speed of the source. We know that if I apply the reasoning, that in the case by analogy with the sound, you know, light going at the speed of sound, so a plane going at the speed of sound should hear a sonic boom. So I can detect violations of the relativity principle. By the same kind of reasoning, when it comes to the Michelson-Morley setup, I should be able to detect what velocity I'm going with respect to this medium of the light, the ether. People just found nothing, and they didn't know what to do with it. And they constructed lots of fancy attempts to explain what was going on. So people thought that maybe this whole detector has to smush around, contract and expand in various odd ways to get the null result. But these were all kind of ad hoc explanations for the null results that they detected. And it was only really Einstein in 1905 who came along and solved the problem, basically by stipulating what we wanted. So what he said in his famous 1905 paper, by the way, Einstein wrote 4 incredibly influential papers in 1905 to do with statistical mechanics, to do with quantum mechanics, and 2 to do with what I'm talking about here, which is going to become the theory of special relativity. This year, 1905, has become known as his year of miracles for that reason. He just revolutionized every field of physics in 1 year. And what he did in this paper is he said, well, let's just think about what we want. We've been looking for violations of the relativity principle. We think that sound violates the relativity principle, but we haven't found any violations. It always looks like the speed of light is the same in all frames in uniform translatory motion, even though we wouldn't expect that based on the physics of waves. So let's just insist that, in fact, the relativity principle does hold. And let's insist that light behaves like a wave. So the relativity principle says what I said before: the laws of physics are the same in all systems in uniform translatory motion. The light postulate says that the speed of light is independent of the speed of the source, which is a fact about waves. What we need to do is to recover or reconcile these two. And basically, we just need to accept that light travels at the same velocity in all frames in uniform translatory motion. What you find is that accepting these two things has some consequences for space and time in ways which are very easy to articulate and which I'll go through. But basically what Einstein did is just say, look, you've got these null results from the Michelson-Morley experiment, just accept it and roll with the consequences. Let me illustrate how he thought in the kind of things that he illustrated in the later sections of this article. So there's some consequences of accepting that if well, let me actually illustrate this with a simple example now. So basically what Einstein is telling us to accept is that if I am at rest and I shine a torch like before, then it goes, I see the light going out at the speed of light. But if I'm in uniform, oops, what happened there? If I'm in uniform translatory motion at some velocity v, then from my rest frame, the light still looks like it's going out at c. So if I'm on the motorway driving along and someone shines a torch next to me, I see that light going past me at c. But even if I were going at 99% of the speed of light, it would still look like the light goes past me at c. That's what Einstein is asking us to accept. By the way, by c, I always just mean the speed of light. Accepting these things, which Einstein is telling us to accept because it's the only way to get around the null result of the Michelson-Morley experiment, leads to some consequences for space and time. So you can illustrate this with the case of what's known as time dilation, say. So suppose I have some clock which works like this. It has 2 mirrors and it has light bouncing between the mirrors. And every time the light hits the bottom mirror, the clock ticks. So light goes up like this and then down like this. And then as the light bounces, let's call this distance L, goes up and then down again, the clock ticks. So you could say that the amount of time it takes for the clock to tick is just given by speed is equal to distance over time. So time is equal to distance over speed. So that's going to be 2L over the speed of light. But now if I think about myself moving with respect to that clock, then, or equivalently, the clock moving with respect to me, so now going this way with some velocity v, then I've stipulated that light always goes at the same velocity. The distance between the mirrors is still L, but now the light has to traverse this longer distance d, the hypotenuse of this triangle. So the delta time for the clock to tick here will be 2d over c, which is bigger than delta t. The point is that if your clock is moving, if you accept everything that Einstein's told us, then it looks, and indeed is, running slower. This is the phenomenon of time dilation. So moving stuff runs more slowly. There's also consequences for simultaneity, which are very odd and worth discussing. So suppose that I am on a train in the middle of a carriage. Sorry, this is kind of a wonky carriage. And I have a torch in each hand. And I'm bang in the middle. And I fire light. And it hits the end of the train at the same time because I'm bang in the middle. Now consider this whole thing, but from the perspective of someone on the station as my train is going through the station, not stopping with velocity v. Well, Einstein has told us that we have to accept that even from the point of view of this person on the station, light still goes at the velocity c. But that means that actually these two events of the light hitting the ends of the train are not going to be simultaneous from the point of view of this person on the platform, because the light's going to go this way, but the train's going to have gone a little bit of further by the time the light gets to the end. Whereas the light that goes this way, the train will have kind of gone towards it. And so the light will hit this end of the train before this end, from the point of view of someone on the platform. This is where the term relativity comes from. Some things which we previously thought were absolute, like simultaneity, become merely relative to one's frame of reference and dependent upon one's velocity in special relativity. Simultaneity ceases to be an absolute fact, but becomes a relative fact. The amount of time that a clock ticks ceases to be an absolute fact, but becomes a relative fact, and so on. And this all follows in a way which is very, very elegant and nice and requires only really GCSE maths, from Einstein's two postulates, the relativity principle and the light postulate, which were motivated by these null results of things like the Michelson-Morley experiment. Why is this relevant to what I'm talking about today? Well, the point that I wish to emphasize is that since the genesis of special relativity, we've had this view that the speed of light is constant and it doesn't depend upon how you're moving. And from that, many odd, perplexing, and fascinating consequences follow. But now I want to kind of skip ahead 10 years to the context of Einstein's general theory of relativity. What's the difference between these two theories? Well, special relativity doesn't say anything about gravity. Einstein wanted to reconcile all of his work in his 1905 theory, telling us about the nature of space and time following from the relativity principle and the light postulate with gravity. But it turned out to be super duper hard to do. I mean, someone could make a movie out of Einstein's mental anguish as he went through various dead ends and conceptual leaps to get to his final completed theory of general relativity in 1915. But I can just tell you the gist here. So the point of general relativity can be summarized in Einstein's, well, not only summarized, but is indeed accurately mathematically summarized and described in Einstein's field equations of general relativity, which say this. Now, what does this mean? On the right is a term, this object T, which describes the material content of the universe. And on the left is a term, this object G, which describes the amount by which space and time are curved. What does curvature mean? Like, you can think about a heuristic analog in terms of, and people often do this when they're talking about general relativity or presenting it in a popular way, consider like a rubber sheet, consider heavy marbles on the rubber sheet. The sheet obviously bends in the presence of the marbles. Roughly speaking, that's what's going on with curvature, but you actually don't need to give some kind of analogy like that. Actually, the definition of curvature is really easy to state, and this is the exact mathematical definition. Think about two arrows, two vectors pointing in some direction. So let's imagine those two things on the equator of the Earth. So two arrows like this, just pointing up. If I can transport those vectors, those arrows along two different paths and then bring them back together again. So suppose I take this one over here, so it's pointing up here. And then I suppose I take them both to the North Pole. So this guy goes over here, be pointing like that. This guy goes over here and is pointing like that. If it's the case that when I transport those two arrows along two different paths, they don't point in the same direction anymore, that's the literal mathematical definition of curvature. And you can easily see from this why the surface of the Earth is curved in a mathematical sense, because my arrows, when I bring them to the North Pole, after transporting them along those two routes, don't point in the same direction anymore. That's what curvature means. And that's what Einstein is claiming is also true of space and time in the presence of matter. This leads to lots of effects. So famously, after Einstein came up with his theory, people thought that light should bend around the sun due to the bending of space and time, due to the warping of space and time of the sun's mass. And indeed, people detected that afterwards. This is the famous Eddington experiment. That's just one of the pieces of experimental confirmation for general relativity. It's obviously still ongoing. So only a few years ago, they detected gravitational waves as well. The point that I want to make now is that we started off with all of our discussions about the invariance of light motivated by Maxwell's equations. Maxwell's equations say that light is a wave. And eventually, by thinking about Maxwell's equations, thinking about the null results of the Michelson-Morley experiment, Einstein arrived at special relativity. But actually, the form of Maxwell's equations changes when one moves from special relativity to a curved space-time setting like that of general relativity. And so it's no longer actually totally obvious that light should behave in the same way all of the time when you move to a general relativistic curved space-time setting. Maybe light interacts with the curvature of space-time such that it doesn't invariably, inevitably, necessarily always go at c. This is something that physicists have thought about for a long time. So one of the more famous physicists of the 20th century was a person called Bryce DeWitt, super mathematical and also insightful person. And he argued that if you think about light propagating in curved spacetimes, in general, it will actually develop what he called tails. So if you have a packet of light, depending upon the curvature of space-time, more and more of it will kind of lag behind the speed of light. This is what he calls the tail. And so if you consider some like photon detector or some other detector of light, depending upon the curvature of space-time, depending upon the situation that you're in, effectively the detector could actually tick later than you would expect, indicating that at least like operationally, light is going a little bit slower than the speed of light. The details here are extremely complicated, but the conceptual idea is, I think, relatively clear. Another group of people who have been working on this very much more recently are two physicists called Asenio and Hodgman. Both relatively, well, both eminent physicists, Hodgman especially so, very well known in the general relativistic community. And they have a more direct approach to this. So they just take Maxwell's equations describing light in curved spacetimes, and they solve them. And it's really, really hard to solve these equations. But you find that at least in some settings, for example, close to a rotating black hole, this is modeled by what's known as the Kerr solution of general relativity. In general, you don't get light going at the speed of light. And in general, light can exhibit what's known as dispersion. It can go both faster and slower than the speed of light, c, depending upon the context. Now, you can say fair enough, but there's this result in physics called the geometric optics limit. Which says when the wavelength of the light that you're dealing with is much less than the scale of curvature effects, you can effectively ignore curvature effects. When you're effectively in the regime in which curvature is negligible, you should recover the velocity of light being c. This is something which people have proved. But what Asenio and Hodgman also say is that not only is it the case that outside of that limit, light in general doesn't go at the speed of light, but also there's something mathematically problematic about that limit. You can't even take it sometimes. It doesn't make sense to think about geometric optics sometimes. That would make the situation even more delicate, because it would mean that, you know, there's not even any kind of appropriate regime sometimes in which light goes at the speed of light. This is where my own work has come in. So I recently published a physics article. In some sense, with my collaborator, Niels Linnemann, who's based at the University of Bremen, in some sense agreeing with Arsenio and Hodgman. So we agree actually that in some space-times, if you solve Maxwell's equations very carefully to describe the behavior of light in curved space-times, it doesn't always go at the speed of light. But we disagree with their kind of claims about this optical limit. We think that you can always take this limit. So whenever the wavelength of light is much, much less than the scale of curvature effects, in fact, light does behave in this normal way. This is all just to say that the situation is delicate, and really you have to get your fingers dirty. You can't just bandy around claims about light transferred from the special relativistic context to the general relativistic context without doing any mathematical work. You actually have to do the work and figure out what's going on. And that's what these people, to some extent, including myself, have been interested in recently. I guess it's the standard philosopher's conclusion of saying, actually, the situation is subtle. That's yes and no is our answer to the question about whether light always goes at the speed of light. Okay, so that kind of takes me to the end of the second part of the talk. Now I just want to say a little bit more about why it's interesting to think about things going at the speed of light or not. So one thing that you might worry about when it comes to things going faster than the speed of light is it might seem to allow for the possibility of signaling backwards in time, which would be perplexing. So let me explain how this one works. I need to draw, to make this clear, I need to draw what's known as a space-time diagram. Hopefully it's not too complicated. So imagine that this is my time axis, this vertical line. This horizontal line is my space axis, and I'm describing the motion of light. So if I shine a torch in this direction, obviously goes a certain distance in a certain time, a certain distance in a certain other time, and so on. I could shine a light in the other torch in the other direction as well. So these would be the paths of light out. And I can also think about light coming into this point. Think about this whole cross. This is known as a light cone, which people often like to talk about in relativity. Now, one of the things which I was talking about before is that in special relativity, simultaneity is relative. So if I'm sitting on my train, I think that the events of the two beams of light hitting the ends of the train, let's call it this event and this event, are simultaneous. So for the person on the train, I could say that these are the facts about simultaneity, this horizontal line. But the person who's on the platform thinks that one of these events happens before the other one. This event over here happens before this event over here. They have a different simultaneity slice. Their simultaneity slices switch, or the simultaneity slices depend upon your state of motion, who you are, whether you're the person on the train or the person on the platform. Now, if you have something going faster than the speed of light, what it's doing is it's following a path like this, say. It's following a path, it's moving more distance in a certain interval of time than light would. So it would be following a trajectory outside the light cone. But then this is kind of weird, because if you just think about this description from the point of view of the person on the platform, actually, it's not moving to the future, it's going into the past. It started at some time here, and as it's gone further and further back from this simultaneity slice. So there's this worry that faster than light objects, tachyons, allow causal propagation backwards in time. Whether that's actually true or whether that would allow kind of signaling backwards in time or anything is a different question, but at least tachyons, faster than light objects, seem to be playing in some weird ways with the causal order which we might like to impose upon the universe. Final thing that I want to say, obviously traveling or signaling, transmitting physical bodies faster than light would be nice, because we think of light as being a cosmic speed limit. It prevents us from getting to places or transmitting information to places any faster than this limit c. if we could, in fact, propagate signals faster than C, that would be lovely. If we could move ourselves faster than C, that would be even lovelier. Some people talk about Alcubierre, I think the name is, drives in general relativity. The idea is that you have a spaceship which is sufficiently heavy to warp the structure of space and time such that it can contract space and time in front of you and stretch out behind you such that you could kind of leap over large distances. All super duper speculative, but this is one way in which you might try to, well, people, just to say that people, I think this was actually NASA funded, that study. People, you might like to think about ways in which you could go faster than the speed of light because you want to get places faster. You want to transmit information faster. So that's one reason why this kind of study is interesting as well. I think it's all super duper speculative going that far down the road. I'm just interested in whether these universal claims are actually true or not. But I hope I've motivated, at least to some extent, that when you actually start doing the physics in general relativity, things which you take for granted are not necessarily so. In my view, that's good philosophy of physics in action. You want to look at every assumption which people make about physical theories and actually think about whether it's true or not. So this is just one example of a wider kind of way that philosophers of physics proceed and they actually engage with practicing physicists. So I've said a lot of stuff. I'll leave things here, but I'm really interested to hear your questions. So yeah, thanks for listening.